Hi, welcome to Prim's algorithm, which is used to build minimum cost spanning tree. Here, the property of Prim's algorithm is we have to select the edge in the set A always form a single tree, right? So each and every edge which we are going to add in the set that should form a single tree. We should not form different trees in the forest. Okay, so now from the given graph we have to identify the minimum cost spanning tree by using the Prim's algorithm. First step, we can select any vertex randomly. So we can select any vertex randomly. Then we have to select the minimum weight edge from that selected vertex, then that add it into the minimum cost spanning tree. For example, if you selected 3, then we can add that into the minimum cost spanning tree. Now that edge which is minimum weight, so minimum weight edge is here we are having 5, so 5 is add into the minimum cost spanning tree. Then select next safe edge, that means next minimum weight edge to any vertex that is already connected. So now we are having two vertices which are already connected in the minimum spanning tree. So from these two vertices, whichever vertex is having minimum weight edge we can select. Suppose if you select the 1, so from the 1 we can select minimum weight edge, that is 1. So now we have selected the edge between 1 and 2, that weight of that edge is called 1. So now we have added that edge into the minimum cost spanning tree. So we have to repeat that step 3 of to visit or connect all the vertices given in the graph. So now you can select again 1 or 2 or 3 to select the minimum weight edge. So from the 1 again we are having one more minimum weight in the given graph, so that is 2 from the 1 to 4. Then you can select another minimum weight edge, that is the 3, which is connecting the 5 from 4. So now we visited all the vertices, that means all the connected vertices available. So we can stop the algorithm. So here we can identify the minimum cost spanning tree by using Prim's algorithm. Here the new edge is always selected based upon the already existing vertices in the minimum spanning tree. We should not form the vertex, form the edge like different distinct components like this. We should not select. So it is not allowed in the Prim's algorithm. We have to select the edge from already connected vertices or edges in the minimum spanning tree. Now we will see the pseudocode. So initially we are taking the set A, which is empty set, that means set of edges available in this A. Then we are taking any arbitrary vertex, randomly selecting the vertex from given number of vertices. Then that is assumed as a U. Here we are using the priority queue so to select the minimum weight edge, so here priority queue is constructed by using the minimum heap, min heap, while a priority queue is not empty, that means it is having the edges. So here we will extract minimum weight edge between the u and v. Already we selected vertex u, so from the u, whichever outgoing edges are there, from that outgoing edges we will select the minimum weight edge. Then after, for selecting that minimum weight edge, we will consume order of v log v, because here we are using the min heap, so min heap will be available in this manner. So here the minimum weight edge will be available in the root. After selecting this, again we have to sort out that given data so that again next minimum weight edge will come as a root. So for that it will take log number of edges. Okay, so this to be done for all the edges, so e number of edges, so that is what given here, e log e, right? So here that E is here cardinality of V. So that's what here we can give V log V for all the vertices. So here once you selected this edge for each vertex, V, the parent of V. So here we have selected the source vertex is U, then we have established the minimum weight edge to the V. So here for V, parent is U. That is what's given here. Parent of V is U. Then add that edge into the A. So initially which is empty. So now added this safe edge into the minimum spanning tree. So this is the minimum spanning tree, empty list. So now U comma V is added into the minimum spanning tree. Then we added that vertex V into the set, because already U is connected, now V is also connected like this. So now this is the minimum spanning tree, so this is added into the yes, right? Then delete that selected vertex from the queue. So here queue is there, so we have to remove that vertex from the queue. Again we have to go back, check the queue is empty or not empty. If it is not empty, then again you have to select the minimum edge which is already connected to this any of the nodes in the minimum spanning tree. Then you have to select that minimum cost edge. So if you select one more edge, so that may be like this, so this to be available minimum cost with the minimum cost, then here that is assumed as a u, this one will be the v, so here the parent of v will be u, right? Again for the next vertex, so here u belongs to s, so s is this one, already s is having two vertices. Okay, so u belongs to s and v belongs to q, unvisited, I mean unconnected vertex. Then you have to make that parent of new vertex will be any one of the node you have selected in the minimum spanning tree will be the parent. Then add that u comma v into minimum spanning tree like this. Okay, so after connecting this, so here any one of the node will be parent, so this new node will become the child. Then add that v into the yes, so new node is going to add here one more node. For example, you take this is v1, so now it is having the three vertices which are connected. Now the newly selected vertex, this one will be deleted from this queue, right? Then again you go back, you check that, so you have to repeatedly do that until the queue is empty. So for this, for deleting, you will take a log v times, okay, right? So on all the vertices you will use the binary min heap, so log v, but we have to select all the edges in the all the minimum edges that is in the graph, so order of e. So finally we will take order of e log v, right? So the time complexity for this algorithm is this one, order of v log v plus order of e log v. So this is the term, so 2 log, finally we will get approximately 2 e log v. So here 2 is taken, so e log v. So this is the time complexity for Prim's algorithm. So as per the given algorithm in the previous slide, first we have to construct the minimum spanning tree from the root vertex u which is available in the set u. Then we have to use the priority queue which is having all the vertices which are not connected in the minimum spanning tree which are available in the graph initially. So we are going to use the all vertices to construct the minimum spanning tree. Then key of v is the minimum weight edge, so minimum weight edge from this u to any other vertices will be selected, so that minimum edge will be selected, that will be added into the minimum spanning tree. Then when you are adding the minimum adding the edge into the minimum spanning tree, you should take care that should not form the cycle. So it should be done until the queue is empty, queue is having the all the vertices available in the graph, available in the graph, right? So it has to be done when you are adding that edge, that should be connected with already existing any one of the vertex in the minimum spanning tree. Suppose if you are selecting the second edge, that edge should be selected from any one of the vertex which are available in the minimum spanning tree. So here the new vertex will be child to already existing vertices in the minimum spanning tree. So here the existing vertex in the minimum spanning tree will become as a parent, and a new node will become as a child. So for this running time complexity is order of E log V when you are implementing by using binary min heap. Thanks for watching.